So, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Quantum Mechanics 2 with the course code PHY 313, we are at the lecture number 16 and the topic is addition of angular momentum in case of composite systems such as a system made of two electrons. This is an important topic because of its practical applications in atomic and nuclear physics, where we often find systems which are composite. In such composite systems, it is important to find out the total angular momentum, which is made of the angular momentum of constituents of the system. In today's lecture, I will explain to you that how we can add the angular momentum of constituents of a composite system and then get the total angular momentum. But I will keep to the example of a composite system made of two electrons. But this procedure can be extended to the case of more complicated composite systems. Okay, to start with, I will first tell you that what is total angular momentum of a composite system. But here we will keep to two simplicities. First of all, I will consider the two electron system. So you can think of a helium atom where there are two electrons revolving around the nucleus, or any shell of the atom where there are two electrons, so you can consider that one. And the other simplicity is that I will not consider the spin of the spin angular momentum of these two electrons or this composite system, and I will only consider the orbital angular momentum. It is straightforward to then extend to the case where spin is also included, but in order to show and describe the procedure, we need to stick to this simple example of two electron system. Okay, so as we know that angular momentum is a vector quantity, which means that we can represent it by an arrowhead. So let's say the angular momentum of the first electron is L1, that is the orbital angular momentum of the first electron of this composite system, because this composite system has two electrons. So the angular momentum of the first electron, let's say it is L1, and it points in this direction. And then we have the angular momentum of the second electron is equal to L2, and this points in this direction. So then if we want to add them to get their total angular momentum, that is L equal to L1 plus L2, so this can simply be done by head to tail rule, where you know that we put the L2 on the head of the L1 and then add them and get the summation. This is a very simple procedure, but in case of the addition in quantum mechanics, this is not so simple, because these angular momentum is an operator, and operators cannot simply be added like this. So in this lecture we will develop the procedure that how we can add the angular momentum of two electrons, where it is also an operator, not only a vector quantity, but it is an operator. Okay, so another thing is, after explaining that how angular momentum could be looked at, like it should be considered as an vector quantity, but when we consider a composite system, there is another complication. So think of the angular momentum of a composite system to be L, and this L is, since a vector quantity, it will have its components. For example, in Cartesian coordinate, it will have Lx its component, or Ly and Lz. So it has three components in Cartesian coordinate system. Now in quantum mechanics, when we want to specify the state of any system, then we specify it with the parameters or with the quantities which can be exactly calculated. Now the problem over here is that these three components of angular momentum, that is Lx, Ly and Lz, are cannot be exactly calculated or determined and simultaneously, and exactly cannot be described or determined. Because Lx is uncertain with Ly because of the uncertainty relationship, and so on. Ly is uncertain with Lz, and Lz is uncertain with Lx. So it means that we cannot use the components of an angular momentum to specify the state of a system. So what we shall do now is to consider some other quantities which can be exactly and simultaneously specified with the angular momentum L to represent the state of a system. And if you remember that this we have already discussed in our previous lectures, that the suitable another quantity which is also made of angular momentum is the square of the angular momentum. So if we consider the square of the angular momentum, that is a suitable physical quantity to represent the state of a quantum mechanical system. So here in this case, since we have a composite system made of 2 electrons, and here this square of the angular momentum which we want to calculate for this composite system, and this L1 is the orbital angular momentum of the first electron, and this L2 is the orbital angular momentum of the second electron. But now the question is that how we can calculate the square of the total angular momentum. So apparently it looks simple, because L square is equal to L1 plus L2 whole square, and one can say that it is just the very simple formula of A plus B whole square calculation. But when you do this, when you open this formula, what you will get the square of the first quantity, that is L1 square, and then square of the second quantity L2 square, and then there is an additional term, that is 2L1 and L2. Now here you can see that we have taken the dot product of L1 and L2, and since these are operators as well, so we will see that this 2L1 and L2 brings in some complications into the analysis that we will discuss later. But at the moment what we have done on this slide is to calculate, is to know that we want L square, that is square of the angular total angular momentum, in this simplicity the orbital angular momentum, and this can be calculated with the help of this formula. And why we are calculating L square, or why we are considering L square? Because of the uncertainty between the components of the angular momentum. Okay, so another question is then that what is another quantity which we shall consider with L square. So we can take Lx, Ly or Lz, anyone is equally good, but usually in literature the Lz is considered with the L square. So how we can find then Lz for the composite system? To find out the z component of a total angular momentum of a composite system, the simple formula is Lz is equal to L1z and L2z, where this Lz is the total the z component of the total orbital angular momentum, L1z is the the z component of a orbital angular momentum of the first electron, and L2z is the z component of the angular momentum of the second electron. Here you must be wondering that how I could simply add the momentum like numbers, because these are the vector quantities, and here I have not used any head to tail rule over here or any operator complications. Then how it is possible to use this very simple arithmetic addition? The reason is that we can just simply add these two angular momentum or orbital angular momentum of first and second electron, is that they are in the same direction. So whenever two vector quantities are in the same direction, for example, if you think of them like this is the x direction and this is the z direction, so these two electrons angular momentum are in the same direction. So when it is in the same direction, then they can be treated like scalars, because when they are parallel, and then the sense of the direction is somehow is not important, because they are in both are in the same direction, and we can treat them like a scalar quantity, and the arithmetic rules of the scalars could be applied over here. So here you can see, because of the same direction, we can just simply add L1z to the L2z, and this is the z component of the total angular momentum. Okay, so this was sort of first part of the lecture, where I have told you that we will be considering two physical quantities, that is L square and Lz, to represent the state of an composite quantum mechanical system. Okay, so once we have got this, the next thing is the in this title of this slide is state resolution and good quantum numbers. So there are 2 points over here, or 2 important concepts over here. The first one is the state resolution, and the second one is good quantum numbers. So what we mean by state resolution and what we mean by good quantum numbers. So we start with the suppose that we have a system which is in the state with definite values of L1z and L2z, and you know that L1z is the z component of the orbital angular momentum for the first electron, and L2z is the orbital angular momentum for the second electron, and this is the state. Now this is the bracket notation for any state, and m1 and m2 are the eigenvalues of these two operators. So m1 is the eigenvalue of L1z and m2 is the eigenvalue of L2z. So it is customary to represent the in bracket notation, to represent the state by the eigenvalues of the operators, as you can see over here, the m1 with the help of m2. Now in this state you can ask a question that whether this state can be further resolved. Now first of all, what is the meaning of this question? What do we mean by resolution? So by resolution we mean that, see, we have two operators, L1z and L2z, and their eigenvalues are here to represent the state of a system, of this composite system. Let's say I bring in another operator, for example L square. So there will be a third eigenvalue. But the question is, if I bring in the third operator, so will the value of the state, eigenvalue of the state, or the state of the system, be changed by another measurement of L square? If it is changed, if the answer is yes, it is changed, then we say then the state cannot be resolved further. But if it is not changed, that is the another measurement, for example of L square, is not changing the state of the system, it leaves it in the same state, then we say that it can be further resolved, and it is connected with the uncertainty principle. But at the moment, the message is to understand that what do we mean by resolution is to make another measurement once you have represented the state with certain quantum numbers, and you want to bring in another operator and make another measurement of some other physical quantity, and if the state already present state is affected, disturbed, then we say that it cannot be further resolved, otherwise it can be done. So the question is, can this state be further resolved? So there are two quantum numbers. So let's say answer this question, that whether it can be further resolved or not. So we know that there are two quantum numbers associated with each electron, that is m1 and l1, where m comes from the Lz and l comes from the L. So and m2 and l2, and let's see if this further measurement, because we have in this state used only the z components and we have not used the angular momentum. Let's say if we bring in the measurement of these L1 and L2, what happens to this state? So the answer lies in the uncertainty principle. So for example, you have a state of a composite system represented with the two quantum numbers, and you want to make a measurement, another third measurement. Now this third measurement is, let's say it is L square. Now since L square commutes with the Lz, then it will not disturb the state, and it means further resolution is possible. But if you choose an operator which actually does not commute with the already measured operators values, then we say that it cannot be further resolved. So therefore the answer or the key point is in the mutually commuting operators. So remember that whenever we have mutually, all the operators whose values we are measuring are mutually commuting, then that state cannot be further that is the complete state, and it cannot be disturbed and it can be further resolved. And if they are not mutually commuting, then bringing in any other next operator will change the state, and we say that further resolution is not possible. And also connecting it to the other concept of good quantum numbers, so all the quantum numbers coming from the mutually commuting operators, we say that these are the good quantum numbers. Okay, so if just to make more elaboration on this point, if we have an atom in the state, for example this one, L1, L2, M1 and M2, so it is not certain that it will be in the same state after measurement of L square. Let's say I bring in the L square. Now since L squared does not commute, if you remember, with the L, so what happens, it follows from the fact that L square does not commute with the L1Z. That's different, because L square could commute with the LZ, but L square does not commute with the L1Z. And here you see we have M1, so M1 is here, and if I bring in the L square, it does not commute, so it cannot be further resolved, or these are the limited quantum numbers, or I cannot bring in the L square's quantum number. So as I have already said that L square does not commute with the L1Z, so it follows that so it is not certain that it will be in the same state, so therefore this state is we are not able to further resolve it. So as I have already said, that the point is in the commutation relations. So whenever we want to determine the mutually commuting operator so that we can determine the good quantum numbers or state resolution, we would like to know the commutation relations of these operators. So let's see what are the commutation relations of these operators. For example, what would be the L1Z with L square? That should be equal to, because we have already said that L square does not commute with the L1Z. So if I put in over here the value of L square, that will be L1Z square, L2, L1 square, L2 square, and this term. And now these are actually three operators, three commutators, because L1Z will go with the L1 square, L1Z go with the L2 square, and L1Z will also go with the 2L1 LZ L2. And what happens that these first two operators, because L1 square commutes with the L1Z and L2, but the last commutator relation is not equal to 0. Actually this is equal to this quantity, and you will be wondering that how this comes out from the this third line comes out from the second line. I leave it as an exercise, but I give you a useful hint how to do this. To give you a hint, please recall the values of these the components of the operators. For example, Lx, that was, if you remember, by definition equal to ypz minus zpy, where p is the linear momentum, z component of pz is the z component of the linear momentum, and py is the y component of the linear momentum, and its formula was equal to minus I h bar del by del z. So this is the formula for the Lx, and similarly the formula for the Ly and formula for the Lz. So these Lx, Ly and Lz are actually these partial differential operators. Now take these values and put in back over here for L1Z and similarly for L1 and L2, and open them up and make all and open this commutator as well, that is AB minus BA, and then there will be some terms coming in which will cancel out, and then you reorganize all the terms and you will end up with this result. So the important point over here is that these two operators do not commute, which means we cannot use them to specify the state of a system, of a quantum composite system, because they do not commute. They are not 100% accurate simultaneously, so they cannot give us the complete information about the system, and we cannot further resolve the system because if you bring in the L square measurement, then it will affect the quantum system. So therefore we cannot use them. These are not the good quantum operators or good quantum numbers. They will not give us the good quantum numbers. Okay, then what we can do is, to find out the good quantum numbers, we can guess upon that. For example, if L1, L2, M1 and M2 are good quantum numbers, so now you know the rule. Bring in their operators and check the commutation relations. If they commute, that is, their commutator relations are equal to 0, then they are good quantum numbers. If they do not commute, then you cannot say this. So these are the eigenvalues simultaneously specified in the state. So that's the actually message, that is the technical point, that if the values can be simultaneously specified, that is, there is no uncertainty, or in other words, if the computation relations are not equal to 0, then there is no certainty. If they are not equal to 0, then there is certainty, and we cannot specify the state these eigenvalues simultaneously. So this state, that is L1, L2, M1 and M2, is to find out that these are the good quantum numbers. What we have to do to check the all commutation relations, because if they commute, they must commute in order to be good quantum numbers. So L1Z, L2Z should commute, that is equal to 0. Then L1Z, L1 square, L1Z, L2 square, L2Z, L1 square, all possibilities, L2Z, L2 square, and all of them must be equal to 0. Now if you want to explicitly calculate these operators, these commutators, then some of them are very simple. For example, if you look at this first commutation relation, then you see that here is L1Z and L2Z, so they are completely independent of each other. And if you remember the formula for the L1Z, that was a partial derivative. So partial derivative acting on something where this coordinate is not involved, because they are totally independent coordinates. So therefore it is very simple to see that this commutation relation will be equal to 0 because of this property. Because whenever we do Z1 and Z2 together, they are totally independent coordinates. So whenever this derivative acting on Z1, that will be anyway 0. So if you open up this commutator, maybe acting on a function of Z1 and Z2, but since when we will act with del by del Z2 on Z1, that will bring it to 0, and this will be 0. So you can use this fact over here in order to determine these commutation relations. But it is an interesting exercise that either you put in the values of L1Z and L2Z or use these hints. But anyway, please try to calculate all these commutation relations and check for yourself that these commutation relations are equal to 0. And if you prove that they are equal to 0, then their corresponding eigenvalues are good quantum numbers. Okay. Then as I have already said that this good quantum numbers are these commutation relations have direct relationship with the resolution of the state. So let's say if we measure L square and Lz and find the state to be this one Lm, so the question is that whether this state can be resolved further. And now you know that if let's say we can still measure L1 square and L2 square and not destroy the eigenvalues of L square and Lz. And how we cannot destroy the eigenvalues? If the commutation relation is equal to 0. If the commutator is equal to 0, that is, they do not affect the value of each other, they are certain, there is no uncertainty, and they are completely certain, they can be simultaneously specified, then we say that the state can be further resolved. So the new state is this one. So now we can bring in L and M, L1 and L2. Lm was already there, but now we can bring L1 and L2, and this will not affect. But this state may not be further resolved. So we cannot resolve this state further, because if we bring any other operator, that might not commute with this. So actual thing is that you now have the recipe, kind of recipe. You know that how to find out that certain state can be resolved further or not, or these are the good quantum numbers or not. You just need to calculate the commutation relations between these operators, and if they are 0, then you say these are good quantum numbers and state resolution is possible, and if they are not 0, then there will be uncertainty, cannot be specified simultaneously with 100% accuracy, and then you can say that these cannot be further resolved and these are not good quantum numbers. Okay, so to show that L1, L2, another example, to give you another example, to show that L1, L2 and M are good quantum numbers, we have to prove that the set L1 square, L2 square, L square and Lz commute. So again, this is the kind of recipe where we can use these commutation relations to prove that some numbers are good quantum numbers, with the help of which then we can specify the state without any ambiguity, and the state resolution is possible. So the complete commuting set of the operators, so this is the L1 square with the L square, and 2L1 L square, and if you check out this, these all operators come equal to 0. So these were the all set. So this commuting set is kind of complete set, because they are all commuting because their commutation relation among themselves are equal to 0. Okay, so far this was the second part of the, so to say, this lecture. In the first part I have to recall, in the first part I have told you that we need two quantities, L square and Lz, to represent the state of the system, and then I have told you that what are the good quantum numbers and how we can find out these good quantum numbers using the commutation relations. And second is the state resolution, that whether state resolution is possible or not, it is again can be checked with the help of the commutation relation. If the commutation relation between them is equal to 0, then resolution is still possible, otherwise not. And now we come to the last part and third part of this lecture, where we see the types of the representation. I mean, when we represent a system, this is not unique. There are not only one set of quantum numbers which you can use to represent any quantum mechanical system. There are many representations. Here I will in this lecture talk about only two representations. The first one is the coupled representation, so-called coupled representation, and another one is uncoupled representation. So two sets of quantum numbers, for example this one L1, L2 and M1, M2, and another one, this is called a coupled representation, and here this because you have this angular this z component of the angular momentum coming in, that's why it is kind of coupled representation. But in here you see that the only one z component coming in and not the second one, or the total Lz coming in, so this we say somehow the uncoupled. So both of them are good, coupled and uncoupled, but the point is that the some representation is actually not the unique and only one representation. We can have more than one representations, and then it's up to us or up to the situation that which one we want to use, the coupled one or uncoupled one. And there are some other representations as well which we will discuss in the coming lecture. And then the eigen states are constructed from these two basic states. So if you want to construct the eigen states for this coupled and uncoupled representation, so remember that in both cases, either it is coupled representation or uncoupled representation, the eigen states are constructed from these very simple and basic states. For example, the first state is M1 L1, this is the first basic state, and the second is M2 L2. So we can construct using these two fundamental or basic states, we can use these two states and we can construct the higher representations from them. So in uncoupled representation, the simultaneous eigen states, for example these set of operators, this is a complete set of operators, L1 square, L1z and L2 square and L2z, and the state, the final state is formed from the product of these two basic states. So remember that these L1 M1 and L2 M2 are our two basic states, and this is the final state, or you can say the uncoupled representation state is formed from the product of these two. So we can always do this, that to form the final representation in terms of good quantum numbers using these two fundamental states. And similarly can be done for the uncoupled for the coupled representation. And here you see that these operators, for example L square, Lz, and L1 square and L2 square are involved. All these are this is the set of operators. Previously in the uncoupled representation this was the set, but in the coupled representation these are the set, and we need to calculate their commutators obviously. And but this is all the final representation is again can be constructed, that is this Lm L1 again from these simple states Lm L1 M1 and L2 M2, where over here you can see the summation runs only on M. And after the this we get after the expanding this L1 Lm and L1 and L2 in the summation with respect to M. Okay, so in today's lecture I have also given you these references. So Lebov is a very famous book. I usually take help from this book to for the quantum mechanics, and then Griffith is also a simple book, but there is another book from Blinder. This is a new book, and it will be interesting to have a look on this. So in summary, what we have learned today is to how to add the angular momentum of for a composite system from the constituents of that system. And we have kept ourselves only to the case of 2 electrons, and this is very practical example, because in many situations we will have a number of electrons there, and we would like to get the total angular momentum, and that could be obtained only if we know how to add the angular momentum of constituents of that system. And there are 3 messages. The first message is that angular momentum is a vector quantity, but to represent the state we need L square and Lz. Reason is that this is a commuting operators, and there is no uncertainty there. The second message is that to check the state resolution or the good quantum numbers to make this representation of the system for the composite system, you need to know which are the good quantum numbers, and for this you need to be able to calculate the commutation relations, and also you can check the state resolution with the help of these commutation relations. And finally the third message is that there are many representation, and one representation is not unique. There is not any unique representation. We can have many representations, and 2 prominent one are coupled and uncoupled representation. In the next lecture we will talk about these representation more, and we will bring in another representation as well, and try to understand that how we can use these representations for some composite quantum systems. With this I thank you all.